Hello fellow physicists. If you've seen my notes for deriving the Lorentz transformations, you would have seen that they were a bit long, a few pages, and involved a fair amount of algebra. So I thought up a quick exam method that's quite simple, that requires you to know much fewer things, and it has less chance of the hairy algebra going a bit wrong. So you have to start off with your two frames. You have two different reference frames. One's moving with the speed v, the other one's stationary. So if you remember your Galilean transformations, that's all you need to remember. So you have your Galilean transformations for distance right there. And all that you have to say is that you know it changes by a certain amount, by a certain factor. So you're going to say it changes by a scaling factor, and we're going to give a scaling factor the name gamma. So we have gamma as our scaling factor, because we know it's roughly the same as Galilean transformations, but it changes with the scaling factor of gamma. Okay, the next thing you need to know is this. So if you have this diagram here with CT on the y-axis and the distance, or x, on the x-axis, light is going to be at 45 degrees, and this is CT over here, light. So you have the equation x is equal to CT, because it's at exactly 45 degree angle. So this line has this equation. The same thing will happen if you have it in a different reference frame. So if that's prime and that's prime, you'll just get a different equation. X prime is equal to CT prime, because it's the same line over there. So you need to know that and this. We're going to put them together now to prove the equation. So what you need to do next is replace t. So you take these equations, and all you do, let's actually move that out of the way, and all you do is you replace t, because we had the two equations. This is the same equation from here, just written in a slightly different format. So all you do is you replace these equations with t. You replace t in them for those. So as you can see, the t here changed to x over c, and the t here changed to x prime over c. Brilliant. We're going to call this equation number 1, and we're going to call this equation number 2. The only thing you need to do next is multiply those two equations together. So this times this, and this bit times this bit, and you get a new equation when you multiply them together. So this times this gives you x times x prime. Gamma times gamma gives you gamma squared. Then when you multiply these two together, you can take these out, they become a common factor, x prime, and it goes into 1 minus v squared over c squared, all squared. It's very simple. You can cancel these out because they're the same on both sides. Oh, both of those. Cancel them out because they're the same on both sides. And if you rearrange this equation and do a square root, you get what you know for gamma. Perfect. And you've proved what gamma is, and these become, instead of Galilean, Lorentz transformations.